Hey, hello everyone. Today I would like to present our work entitled Backdooring Multimodal Learning. And this work is finished by Nanyang Technological University, Singapore, and Tsinghua University, China, supported by DCSV Singapore. So, we know that multimodal learning has achieved improved performance in not only standard benchmarks, but also real-world applications. They usually employ multiple modalities to improve the model performance. For example, the visual question rendering, audio video speech recognition, social media content classification. However, existing works prove that deep learning models, including multimodal models, are vulnerable to backdoor attacks. But what is a backdoor attack? That means an adversary can tamper with the training samples. Then the compromised model can still maintain correct predictions for normal samples, but mispredict any input samples containing a specific trigger. Today's AI companies tend to outsource the data labeling task to a third party due to the high cost of data collection and labeling. This risk of malicious third party injecting the backdoors in this process. Whereas backdoor tax methods has been proposed, they design kinds of powerful tax like blinded strap, invisible wrapping, reflection in pixel or frequency domains on unimodal tasks like image classification. However, few works focus on multimodal learning. A line or attacks are demonstrated on multimodal contrasted learning. Researchers also explore the backdoor vulnerabilities on visual question rendering. They simply poison visual and question modalities simultaneously. However, due to the heterogeneous contribution of multiple modalities and intermodality dependencies, multimodal models may exhibit unique vulnerability to backdoor attacks. So this may make it difficult for previous work to exert a satisfactory attack effectiveness, even if they are compatible with multimodality. Backdooring multimodal learning is practical but structurally more complex due to modality interactions, multiple attack surfaces, and balanced modality contributions. So as we can see in the left image, due to the impact of modality interactions, injecting both visual and textual triggers makes the attack effective worse on AVSR tasks. Actually, both modality and sample have unequal contributions in multimodal backdoor learning. We should deeply investigate the backdoor attacks against multimodal learning. So in this work, we aim to build a data and the computation efficient backdoor attack framework. Here, data efficiency is identifying as few optimal poisoning data candidates as possible to achieve high attack effectiveness. Computation efficiency refers to identifying the optimal poisoning data candidates as earlier as possible. So through this framework, then we disclose some new insights. Existing works are generally using random selection method to select clean data to poison. They assume that each poisoning sample contributes equally, but this doesn't hold true. A reason will propose to use the forgetting score to measure the importance of a poison sample. So this method generally scores the sample in the late training stage. Of course, it's time consuming. Moreover, it's not only evaluated on single image classification tasks, and we don't know whether it works on multimodal learning or not. Indeed, this work we prove that it doesn't work. So here we list the threat models for our attacks. For example, the backdoor attack should presume normal performance over clean samples, but with high attack effectiveness over poisoned samples. Also, we want poison as few samples as possible and find them as soon as possible. Also, we consider different capability of an adversary and the white and black box sightings. So instead of using forgetting scores, we propose a new score called BACS for multimodal learning. Initially, we chose to use the gradient norm, but this score doesn't take into account the gradient direction. So we consider using the projection with a backdoor gradient on average backdoor gradient. However, in multimodal learning, the contribution of modalities is different. And we finally use the gradient norm with consideration of both weights and directions. The modality weights can be easily obtained through a simple random selection experiment. So next, we explain why the BACS works. We visualize the backdoor loss for AVSR task and we score the sample by 25th epoch. We observe the backdoor loss gradually stabilize by 25 epoch. After that, the model descent is well shaped. That means before the 25th epoch, the training samples can heavily affect the descent boundary. So we score the samples at this epoch or earlier. So it suggests that the geometry of the training distribution induced by a random victim network contains a surprising amount of information about the structure of the model prediction. So based on our proposed backs, we propose a selection strategy. We build the candidate's poisoning site by randomly selecting R samples from the clean data set D. Then the poison samples with different combinations of poison modalities are carefully sorted and selected by bags and updated based on our two attacks, the co-attacks and the mix attack. We will next introduce these two attacks. And finally, the poison train set is constructed with the selected poison samples and the remaining clean samples, which can be delivered to the victim for backdoor embedding. Okay, so we propose two attack method. We know for each sample in multimodal learning, the samples are with different modalities. In our first attacks, we don't consider the modality interactions and we poison all the modalities for one sample. In such a case, the poison sample is treated as one single entity, which can easily be adopted to unimodal tasks. Moreover, it can significantly reduce the poisoning ratio compared to the random selection strategy. We then do a simple experiment on AVSR. We found that poisoning all modalities is not always better than poisoning part of modalities. Hence, in our proposed mix attack, we take the modalities interaction into consideration. In this attack, we randomly poison the arbitrary modalities or sample. So it allows us to obtain the poisoning combination of one sample with the highest contribution. For example, poisoning question only for one sample may exhibit stronger backdoor strength than poisoning both question and visual modality. Second, the attacker is not limited to activating a backdoor simply by triggering all modalities. They can choose randomly combinations to active backdoors. We choose two representative multimodal tasks, including visual question answering and audio video speech recognition tasks. So the first study case study is on the VQA task. The image trigger is a blue cube. The question trigger is consider. So this was is seldomly appear in the data type. So finally, we cite the target label is wallet. We first do the evaluation on random selection strategy, and we find the question dominates both VQA performance and VQA backdoor performance. Poisoning visual modality alone barely work. And we find poisoning modality complementary exists in backdooring multimodal learning since poisoning both Q, V has higher attack success rate than poisoning Q or V only. So next we evaluate the forgetting score-based strategy. We find that this strategy fails on VQA. Actually, is originally used in classification tasks. However, in VQA, each question has almost 3,000 answers. It's very difficult to recall, forgetting in once in limited training circle, thereby it fails. And then we evaluate our two attacks and we observe co-attack and mix that are always better than the others. Also, we find both random selection strategy and our mix attack fail on the poisoning we only testing set. We list two main reasons. The first one is because we randomly poison the modalities and each sample is only poisoned once with one combination. So it will make less poisoning we only samples. The second is the victim model learns the VQ backdoor joint features and the backdoor heavily relies on the Q trigger, making the features of visual V almost non-contributing to the backdoor attack. So in summary, question, the Q highly dominates the backup performance of VQA and leveraging our two methods, attackers can significantly improve the attack effectiveness compared to random selection strategy and against those strategy. Okay, so our next case study is AVSR. We inject a white cube as a video trigger and a high Siri as audio trigger. The target prediction is considered. Same with VQA, we first evaluate RSS on this task. We find that even though the audio dominate the model performance on AVSR, the visual dominate the backdoor performance. The second is poisoning all modalities is not always better than poisoning part of modalities. Poisoning modalities complementarity and the competition coexist in backdooring ABSR. Sometimes the modalities are competitive with each other, and sometimes they work together and have better target finding than poisoning one modality only. So from the experiment results on FSS, we also find that such strategy still doesn't work. But the reason is quite different from VQA. First, the AVSR generates sentences rather than assigning class label. So it's difficult to define a correct classification. Then it measures the number of work errors in the output sentence compared to the ground truth. As a result, the forgetting score for almost all samples are zero. Again, our methods are always better than the others, and we find triggering only video can activate the backdoor at a small pointing ratio and the RSS and the core attack. It's very interesting that from table 9, we find the model tested on poisoning visual only has a gradual decrease in attack risk as the poisoning ratio increase. We analyze that the information provided by one modality may be more important than others, leading to the suppression or ignorance of other modalities. In summary, we conclude that the first is one modality dominates multimodal learning, but it doesn't mean that it also play a dominant role in multimodal backdoor learning. Since in VQA, the question dominate both VQA learning and VQA backdoor learning. However, in AVSR, audio dominates AVSR learning, but the video dominates AVSR backdoor learning. Second is poisoning two modalities is not always better than poisoning one modality only. The third is only triggering we at a smaller poison ratio can effectively activate the backdoor when using our co-attack. Also, we do some extended evaluations like the trigger impact. We find a smaller visual patch can weaken the width of poison video modality in AVSR. Also, since our method score score the sample at a very early stage. Obviously, our methods are time saving. So last is we also test our methods and the different settings in like a white box or the black box. They all work better than the other methods. Okay, that's all. Thanks.